How's everybody doing today? Cool. So my laptop isn't working right now. I got to get a new one of these, I guess. It's just broken. So we're going to do everything on the board today, but the contents are still in your lecture slides. So the most recent lectures that I've uploaded, it's just going to be Bernoulli's equations with applications. So what I'm going to do is I'm just going to teach from the notes, but I'll do everything on the board and we'll just go over it like in detail like we always do. So we talked about Bernoulli's equation last time. And now we're going to do a bunch of applications because you're going to have to know how to use this to solve problems on your homeworks and potentially on an exam. And so let's just go over what this is. So we've got two different pressures and two different velocities of a fluid. And we derived this last time by using Newton's laws and applying it to a section of fluid that has two different pressures applied to it. So the idea is that you have this pressure at some volume in a fluid, and then on this face of it, it's P1, and on this side, it's P2. And then you have F equals MA, but then what's our force? Pressure times area is our force, so we have a pressure 1 times an area minus a pressure 2 times an area equals mass times acceleration. And then we did the acceleration for the fluid element. That was just given by our kinematics equation for our initial and final velocity. Let me just put that on the board really quick to remind you. Okay. So it was given by, so if we have V2 squared, that's equal to V1 squared plus 2A delta x, where A is in the same direction. So we have some acceleration going in this direction. So then we can have V2 squared minus V1 squared divided by 2, and delta x is giving me my acceleration. So that just goes in this side here, and then my mass, I just do mass in terms of density per unit volume, and then that was volume was like equal to like a delta x times an area. So I had these expressions for all of my terms. There was an area that cancels out, and that's what gives me this equation. Okay? Yes? Question? Sorry. So let me write this a little bit bigger. So we've got force is equal to mass times acceleration. And then what we do is we look at the force on two different sides of this fluid. And we see that the force is going to be a pressure this way and a pressure this way times an area. That's my sum of my forces. So I have a P1A minus P2A. And then that's equal to rho times V, because mass, or I'm sorry, rho V, sorry. Because we have mass is density times volume, because rho is mass per unit volume. Okay, so this should be rho V. Sorry about that. Okay, so then we have rho V times, and then we have acceleration on the other side. So we have to relate this side to this side. So we have rho is my density of my fluid. That just stays the way it does. But then volume can be expressed in terms of something else, can't it? What can volume be expressed in terms of? It's the flow rate times my area. So I have an A times a delta x, because I have this much delta x covered and this much area, that times that gives me a volume. So then I can express volume in terms of that. So we have an A delta x here. And then my acceleration, I used kinematics equations to express the acceleration in terms of a velocity. So I can factor this out, and I have v2 squared minus v1 squared over 2 delta x. That's going to be my acceleration. And then my delta x cancels out, and then I have area on all three sides. That cancels out too. So that combining terms then, that's how I get this. P1 plus 1/2 rho V2. See, I just moved one of the negative signs over to the other side and distributed. So here we have it on both sides distributed out like this. So that's how I derived that equation. Anybody have any questions about this derivation or how I got to it? Okay, cool. So now we're going to do another example. So the first example we did was we had water flowing through a pipe, and it constricted the flow because the area of the pipe diminished. So it had like, started out with some initial area, and then it narrowed in because there was like buildup along the sides of it. And then we wanted to figure out what was the velocity at this point. So we found that the pressure was actually less here than it is here, but the velocity was larger. So now we're going to explore that some more in these problems, these applied Bernoulli's equation problems. So let's do another example. So we've got this aortic distension. It's called aortic, let's see. So if your aortic valve in your heart, that's the left ventricle where your blood exits. If it becomes narrowed, so you have some buildup of plaque in your heart, okay? One of the diagnostic criteria to find that, you go to the doctor's office and they look for a drop in pressure as the blood traverses the valve. So they want to see, okay, we have this instrument, we can look at your blood pressure. If we have a drop in pressure as the blood is going through, so we've got blood, now we're talking about an artery. And the pressure is going to drop here. It's going to be smaller here than here. We have a problem. That's going to indicate that we have the potential for a blood clot or a heart attack, depending upon which region we're talking about, or a stroke, all those things. And then if the pressure drop exceeds 40 milligrams of mercury, a diagnosis of severe aortic stenosis is warranted, and clinicians can use Doppler echocardiography, a form of ultrasound. So they bounce sound waves off of the body in that region, and they measure the speeds of the blood upstream and downstream of the valve. So by using a combination of the Doppler effect, you basically shoot a wave and you can measure the speed of something. Just like a police officer can measure the speed of something using a Doppler, like for like a, radar, shooting radar. They do the same kind of idea, except they use an ultrasound. So they use this ultrasound and they say, okay, what's the velocity of this? And remember, a higher velocity equates to less pressure. So they measure the speeds upstream and down speed for the patient, and then the speeds can then be used to compute a corresponding pressure drop. So in one patient, as the left ventricle is ejecting blood, measurements show speeds of 1.1 meters per second upstream of the valve and 3.5 meters per second just past the valve. Okay, so we have our velocities, V1, 1.1 meters per second, and V2 past the valve is going to be 3.5 meters per second. And the question is, does this pressure drop exceed 40 milligrams of mercury? Millimeters, I should say. Hg. Does the pressure drop exceed that? And remember, we talked about how this works, right? We have a we have an open container of mercury, and the mercury responds to a change in pressure, and it changes, and it rises a certain height in regards to a pressure. So whether the pressure goes up or down, a pressure change is going to affect the height of this column. That concept was tied into our earlier observations about pressure in fluids. So don't forget where that comes from, because that's also important. Okay, so, and that's how it's measured medically, is in millimeters of mercury. Even though it's actually in pascals, the amount of pressure on the fluid rises the mercury a certain amount in millimeters. So you can measure it in units that actually has nothing to do with pressure directly. It's like the indirect effect of the pressure causes the rising of the mercury. Does that make sense to everybody? Because I know that's kind of confusing, right? Like, it's like they're measuring the amount of pressure in how high something goes. But it's not that hard, right? It's kind of like this concept of, like, if you hit something with a hammer and then the force of the hammer causes something to spike up, like those games at the amusement park. It's the same kind of idea. The amount of pressure causes it to spike up or down, depending. Okay, so we can use this, these two velocities, actually, to compute the drop in pressure, because the delta P is just P1 minus P2. So all I have to do is just move some stuff around. I can move this over to here, and then I have I'll move this one over to this side. So I'm going to have P1 minus P2. So this went over to this side. And then that's going to be equal to, and then I'll just move this one over to this side. 1/2 rho V1 squared minus V2 squared, because I moved this one over to this side. And then I have my two velocities, 1.1 and 3.5. And I don't know what either one of these pressures are, but I'm only interested in a change in pressure. So I don't care to solve, I don't have to solve for each of these independently. I'm only looking at the difference. If I know the density of my blood, that's all I need to know to finish solving this problem. It's actually pretty easy. And we do know the density of blood. It's almost the same as water, except it's a little higher, 1,050 kilograms per meter cubed. So I have this is equal to 1/2 times 1,050 kilograms per meter cubed. And then I have my velocities. It's 1.1 squared minus 3.5 squared. Okay. So that's very easy. And then I get that, that's going to be my delta P. So if you plug that into your calculator, you get the result, and it's going to be 3.5 minus 1.1. So let's see. Did I do it the reverse? I flipped it. Okay, so it should actually be 3.5 minus 1.1. Okay. And these are both squared. Okay. So let me take a look at this and see why I got them reversed. Okay. So we've got V2 minus V1. So let's see. Okay. Okay, yeah. So it should be reverse of that. V2 minus V1. There we go. Okay. So that tells us the drop in pressure, P1 minus P2. And it's going to be, so what's our units? We've got meters per second, and then we've got units in pascals. So it gives us units of 5,800 pascals. And then I'm not sure actually, so this is 5,800. They must have looked up somewhere in the book where the conversion is from pascals to millimeters of mercury. But I wouldn't expect you to memorize that for the exam. If I put that problem on there and then I ask you for millimeters of mercury, you'll get full credit no matter what answer you put. But I'm not going to do that. I won't forget to include anything that you need on there for that problem. Pascals is fine, okay? And maybe in some of the homework questions, it wants to know it in terms of mercury. There's got to be a chart in your book, a table in your book somewhere. So it's no big deal. But if you put that answer in pascals, I'd count it as 100% correct. I don't care if it's pascals or millimeters of mercury. But anyway, that's how you solve that kind of a problem. We don't have to know necessarily all of these variables if they just care about a change. They could do the same thing too. They could also say like, okay, what's the relative difference in velocity for this process if I tell you the two different pressures? Then you can solve that too. Yes? I'm sorry, what's that? No, pascals is SI. Pascals doesn't have to be converted. Atmospheres has to be converted. Pascals is automatically in units of pressure that includes newtons and meters squared. Yes, pascals is our SI unit. Atmospheres and millimeters of Hg, those two are the ones that are not. Scuba divers like to use atmospheres, and other industries, maybe aeronautics and stuff, and medical like to use millimeters of mercury because that's their device. But in both cases, our starting point is pascals. If you have your answer, this Bernoulli's equation, the way that it's written, where you have the density of the fluid in terms of however many, kilograms per meter cubed, and you have, as long as you're in meters per second for velocity, meters cubed for density, mass, kilograms per meters cubed for density, pressure will always be in pascals. So if they give it to you in atmospheres, convert to pascals when solving for velocity. Pascals is what you always have, where you don't have to worry about changing it until the last step. Okay, any more questions? Good questions. Okay, so the significant increase in speed and drop in pressure is important to assessing a person's condition. So now you can see how they talk about when they have ER and they get a patient in the hospital, the emergency room, and their pressure's dropping, their pressure's dropping. Now you can see why it's an emergency, because everything that revolves around an immediate person's health involves the blood, right? The blood gets the oxygen to the brain and all the other cells. That's the purpose of the blood, is to transport oxygen and other nutrients, but primarily oxygen first and foremost. If we have a drop in pressure, the blood's not getting somewhere. If it's not getting to the brain or the heart, we have a huge problem. We have instant death because we have to have a constant supply of this oxygen. So this pressure, these Bernoulli's equations, they actually play a pretty big, important role in the fundamentals of medicine. Probably if you're a medical doctor and you go into vascular surgery, right? You probably are going to take some classes that are going to have Bernoulli's equation as a starting point, and then they'll get more complicated, right? You just tack on a layer of complexity, but you always start from this basic premise. So this is your starting point for understanding the blood. Okay. Now, it's important to note, where does Bernoulli's equation get more complicated? It doesn't apply for a fluid that has friction-like viscous forces. And most fluids do have viscosity, including blood. And so, we're not done yet. We're going to extend this Bernoulli's equation, and we're going to get a little more complicated. So, just to start with, we have this chart of viscosity and the viscosity of fluids. And you've got it's table 9.5 in your notes. We've got air, 1.8 times 10 to the minus 5, all the way to motor oil, that's at 20 degrees Celsius. That's 2.4 times 10 to the minus 1. So you can see here, viscosity of a fluid, what that is it's the tendency for the fluid to run into resistance to its own flow. It's sort of okay, if I have honey is a fluid, and so is water. Why does water pour so much easier than honey and so much faster? Because honey has a much higher viscosity, it's thicker, it forms these layers, they bump into each other at a molecular level. The flow isn't smooth, it's turbulent. It's got a lot of resistance to its own flow, so it's moving along real slowly. So overall, the viscosity is sort of like this thing that drags on a fluid and slows it down. And we can incorporate that into a flow equation that works for like things like blood and gives an even better picture of the dynamics than Bernoulli's equation. Not that Bernoulli's equation isn't good for its purposes. It works really well for some things, but sometimes we want something more precise. So the explanation for it is the fluid moves fastest at the center of a tube when it has viscosity. The center of the tube, it goes the fastest. And then it decreases away from the center until it reaches 0 on the walls of the tube. Because the layer of fluid in contact with the wall of the tube does not move at all, whether it's water moving through pipes or blood through arteries. The fluid at the edge lingers and barely moves, and so it builds up along the walls. What's actually happening is there's electrons that are interacting with the walls, and the electrons come from the fluids. And the electrons don't really interact with the other electrons in its own fluid. It's like, I don't really care about you, you're just like me, I don't care. But if I'm close to the wall, I care about those electrons in that wall, and I interact with the wall more, and that slows me down. And meanwhile, my counterparts that are more towards the center, they just fly right past. So that's sort of like the microscopic picture of the mechanical aspect of viscosity. To give you a more precise explanation, we have to start getting into like a little bit of like quantum stuff. Although most of it can be explained with like classical mechanics actually. But, well, classical mechanics and electrostatics. Okay, so we've got this picture of an ideal fluid. It's like the velocities of the ideal fluid in the tube, they're all the same. It's just like 1, 2, 3, 4, 5, where that represents the magnitude of my velocity at any given point. But then, if I have like viscosity going on, that's going to completely change that. So the viscosity is going to look like this. It's going to be like smaller on the edges, smaller, and then there's like a gradient where it gets largest at the center and goes back down again to the walls, it's less. So it looks more like that for a viscous fluid. And it's essentially 0 on the sides of the wall, so we could make that a lot smaller. But not totally 0. It could have some velocity, but a lot of times it is like pretty close to 0, like it just forms like a film over it. And that's a problem that sort of explains the basic idea of how plaque gets deposited into an artery by the very blood itself that's supposed to be transporting it too, doesn't it? Because there's particles, and there's still a lot of debate in the medical community of how this arises. But like the typical answer you'll get from your doctor is, well, if you eat a lot of fat, right, the blood carries the fat, and then the fat particles, like they get, if it's carried by this, happens to be carried by this blood, the fat like gets stuck to the walls because it's going so slow that it has time to deposit fat, whereas the fast-moving blood just carries the fat wherever. So don't eat a lot of fat. That's not actually correct, because your intestines and your stomach has enzymes that completely digest the fats and put them into a molecular level where they don't behave like oil in a like pouring like bacon grease down a drain. But what it's more like is if you eat some other things like sugars, right? The sugar molecule interacts with the fat, and that causes a type of process where it makes it stickier, and then it sticks in that process. But yes, the viscosity of the blood, one way or the other, it does increase to the effect of the artery getting clogged over time slowly. But the process is a little more complicated than just that simple explanation of fat. It also depends on what kind of fats we're talking about too. But anyway, that's the basic idea there. Okay, so we can't characterize the flow of a viscous fluid by a single speed like we did with Bernoulli's equation. So that's kind of a problem, right? How do we explain a flow of a viscous fluid at two different points if our V's are not the same? Not only across from here to here, that's easy enough, but they change from here too. It's like the V along this area is different. It's not the same here as it is here. In this picture with Bernoulli's equation, V1 is the same across this entire area. So that's the fundamental complication that we're dealing with our differential equation. We're trying to mathematically describe how do we incorporate that gradient of velocities into our equation. But we do remember that we have an average flow speed. So we think about this like as in cars. Like we have some cars on a highway, and we'll pretend that the fast lane is this lane in the center. Sometimes it does work like that with the highway. You have the lane going fastest in the center, the carpool lane's clogged up, it's barely moving, and the lane where people are merging onto the highway is going really slow. But in the center, it's going fast. Okay, we can characterize the average flow speed of that traffic by a flow rate equation like we used before. We have this Q is equal to, so this is our flow rate, remember, Q is equal to delta volume per unit time. And that's just conservation of flow. That's still going to hold. Why does conservation of flow still hold? Because, remember, this fluid is incompressible. So if I push fluid along in a certain amount of time, the same amount of fluid has to flow through this point as this point per unit time. And that holds whether or not all the fluid is going the same velocity or if it's going at different velocities. So that's our first little trick to dealing with this new complication. We note that the flow rate equation still holds. The next idea is that we have this Q is equal to VA for an ideal fluid. So if we have Q is equal to VA Q ideal, what is Q going to be for an average fluid? Well, it's going to be Q average is V average times A. So V average is going to be Q average divided by A. Or just Q, because Q doesn't change. So that's another thing. Oh, we don't have to do a Q average because Q equals Q no matter what. So that gets rid of that distinction. Okay, so then the next thing is we've got this situation for the pressure gradient needed to keep a viscous fluid flowing. So if fluid flows smoothly with an average speed V average through a horizontal tube that has a constant diameter R, if it's an ideal fluid, we have that delta P is equal to 0 because there's been no change in the area, so there's been no change in the velocity, so there's been no change in anything. So A1 equals A2, and delta P is equal to 0 in this case, where all the fluid is flowing at the same velocity. That was before. That was our ideal fluid. So there's no net force on this segment of fluid. It simply coasts through the tube at constant speed with no change in pressure. It's like a puck gliding across a frictionless surface. Makes sense because viscosity is a lot like friction. Okay, but if there's friction, something has to apply a steady force. Remember, friction is a force. So viscosity then, we would expect that to be a force as well. So our reasoning here has to be going back to Newton's laws. This is the case where there is no force, no net force, so no change in pressure, so everything's just 0. No forces. It's like the sum of the forces is 0. Static condition. Here we have a dynamical situation where there will be a change in forces. So the pressure difference between the ends of the tube is a pressure difference needed to keep a viscous fluid flowing. So if I have viscosity here, I have a pressure difference. There will be a pressure difference needed to keep it flowing. So I have to describe this pressure difference from here to here at these two different points. and then I have the pressure force on the segment of fluid in a tube then is going to be given by, let me see here. Okay, so the pressure difference is going to be given by A times delta P. So pressure difference is going to be given by A times delta P, where delta P is the change in pressure associated with these changes in velocities. Because remember, if we had two points in a fluid where there was a velocity difference, one's going faster than the other, then there was a pressure gradient. So now there's going to be a pressure gradient across this region here and this region here. So the delta P will exist in this region, not along this way necessarily, but just along this way. So we need to have this pressure end be between the ends of the tube as well, and there's a pressure needed to keep it flowing. So the pressure force is just A delta P, where A is the tube's cross-sectional area. And then the drag on a sphere of radius r moving through a fluid is given by this value here. Now, okay, so for this derivation, they go all the way back to something that was like in last quarter. So it's like chapter 6 when you're talking about friction. And they're talking about a sphere. They're saying, okay, if I have some solid sphere and it's moving through a fluid, there's going to be fluid particles that are going to bounce off of this thing, and they're going to slow it down. And then it's going to feel a force. You could think of it as kind of like air resistance. If you drop the ball and the ball goes through the air, right? It reaches terminal velocity. It doesn't just keep speeding up and accelerating. At a certain point, it reaches a constant and steady speed of like a little over 100 miles per hour as it's falling from the sky. That's the same idea here. The wind pressure, in this case, it would be if it's falling down, the wind's going up and around it and everything. But either way, it produces this drag force that's given by like this value 6 pi n VR. Okay, don't worry about where they came up with that from. I don't want to spend a whole class explaining what each one of these terms is. But basically, it's just like, okay, that's our drag force. You don't have to memorize this, and you don't even have to know what these terms mean. I promise you, I will not put this on the exam. The only thing that you're going to need to know how to do is solve for the equation that this comes from. But just know that this is the friction associated with like an object that we would place in this fluid. Okay, so it would seem that the viscous drag on a segment of fluid flowing through a tube would be similar to this. It would be some constant times n times V average times L. Because these terms here, this 6 pi, comes from spherical geometry. And here, we don't have spherical geometry. We have like a cylindrical geometry. And so instead of it going along some radius, we expect it to go along some length L. So replace the radius with an L, and then we're going to keep our N and our V, because those are constants associated with the substance. N and C are going to have to be something you just like look up in a table. It'll be different for water versus oil, etc. And V, we just replace that with V average, because now we're not talking about one object moving. We're talking about the whole average parcel of fluid. So in other words, I'm saying, okay, I'm dividing this fluid up into like a little piece. But even within this little piece, I have a differential amount of velocity change. So I take the average velocity of that, and I incorporate that into my drag force. So this is the drag force associated with my fluid. Now what I have to do is I have to actually figure out what the C is. And what I can show is that C is equal to 8 pi. that has to do with the geometry of the cylinder. So then this C, that now the only thing that I have to know is the N coefficient for the fluid, which has to be measured experimentally. There is no analytical way to just magically plug something in for that. You got to go to a laboratory and you just have to measure that for all these different substances. Okay, so let's say we did that. Now, the steady motion for the fluid occurs when the pressure force balances the viscous drag force. What does that mean when I say steady motion? It means that the forces have reached an equilibrium. It's moving at constant velocity. If it's moving at constant velocity through this viscous process, it's moving, right? But if it's moving at constant velocity, is it accelerating? No, which means the net force on it is zero, which is just like when you go skydiving and you reach terminal velocity. You're falling downwards, right? You're going down, but technically you're not accelerating because you stopped accelerating because the drag from the wind balanced out the force of gravity, so your net force is zero. Yes, you still have a velocity, but since that velocity is no longer increasing, your acceleration is now zero. So F equals ma, it actually still equals zero, even though you're going very fast. That's the idea here. This fluid gets moving and it gets going and it accelerates, but pretty quickly the viscosity acts against itself and it reaches a constant steady flow. That's kind of makes sense then. It's like, okay, that makes sense. That's why when I dump something out like a heavy paint, it's like at first it starts to flow fast, but then pretty soon it drops and it's steady. And then no matter how much I hold it, it doesn't speed up or slow down. It's just like the same amount of paint flows out of the can per unit time. Same idea here. So that's all that we're saying. So we can write that in Newton's law because we have F equals ma, and then we're just going to sum the forces of the friction versus the pressure difference. And we're going to describe both of those in this equation to actually derive the viscosity equation. Okay, so we have delta P times A. That's going to be equal to the force from the pressure that divided by area. Okay, so let's see if we can make sense of this. And remember, this is a net force. So this is a sum. Because I have P1A minus P2A, that's what delta P actually means. That equals the sum, which is the pressure over the area. Okay. So then for a circular pipe, A is pi r squared. So it's going through this area here, which is pi r squared. A is equal to pi r squared. So we have pi r squared there, and then we can find that the required pressure difference to move the fluid at the given speed, V average, is given by this. So we had this pressure force. Then that's going to be equal to the other force, which is from the viscosity. Okay? And that's going to be equal to pi r squared. Now I want to emphasize, these forces are not the same. This is two parts of the same equation. It's actually F pressure over some area across this tube minus F drag over pi r squared equals 0. Okay? That's the actual Newton's law equation. We sum the forces in both directions, but then we realize that that's going to be 0. So it's like, oh, okay, I could just move one over to the other side, and then I have this. But that's where that comes from. These two terms are not the same. It's just this minus this equals 0. They come from different things. This comes from the pressure gradient that exists because we have different velocities along this direction, this area here. And then this one exists because we have a frictional force at different points along this pi r squared area. So then when we set those equal to each other, we can set that equal to what I had from above, where I had that 8 pi n v average L. So we have 8 pi n v average times the length of the pipe, okay? But my pi's are going to cancel. So that's going to simplify a little bit more. And I'm going to have this result left over, where I have the pressure gradient, delta P, which is actually P1 minus P2. That's going to be equal to 8N V average times L over that R squared, where my pi's canceled out. So that's going to bring us a lot closer to a frictional viscosity equation. Okay, then we can solve it for V average, and we figure out what V average is in terms of the pressure differences. So I just rewrite that up here, and then I move this over for V average. So I'm going to have R squared times delta P equals, and then I divide by 8NL equals V average. Okay. So does everybody see how I got that? Does that make sense? Anybody have any questions about that? Okay, cool. So then the viscosity is in the denominator, which tells us that the more viscous fluid flows, the more viscous the fluid is, the more slowly it flows. So the V average, this N is going to get bigger for more viscous fluids. So if I give you like a list of like fluids, right? And I'm like, okay, N1 for fluid 1 is 10, N3 for N2 for another fluid is like 1,000. Which one has a higher or lower velocity? You can tell just by plugging those in. You can see which one's going to flow, how fast it's going to flow based off of that. So then, and then let's not forget that we still have our volume flow rate. We still have that Q volume flow rate equation that we started with. Maybe I erased it, but it's just to refresh your memory, right? It's going to be volume for, you know, some area. So we have V average times some area. That's a volume flow rate. And then we know what that is. It's pi r squared. Pi r squared, because that's the area of my tube, times V average. So I always have this to work with too. So then I can substitute that last expression for Q. Because look, I have Q is equal to V average over A. So V average is equal to Q over A. So I can just rewrite this expression in terms of Q for my volume flow rate. So I have R squared delta P over 8NL, and then I just have Q divided by A for that. That's equal to Q divided by A. And then I can just move A over to the other side, because A is going to be pi r squared. So A is pi r squared. Move that over to the other side. That becomes r to the fourth, and that becomes pi. And that's going to be the equation you see in your book. Q is pi r to the fourth times delta P over 8NL. That's Poiseuille's equation for viscous flow in a pipe with pressure gradient. And you'll use that to solve all these types of blood problems, where we have like the viscosity of blood is given by this, figure out various quantities, drop in pressure, etc., etc. Now you know how to get that. All that we did was we just took the case where we have an object flowing and it's reached a point where the force of friction is equal to the pressure difference across the fluid. So to reiterate, a pressure difference is always caused when we have a difference in fluid flow velocities. If we have different fluid flow velocities from here to here, then we have a pressure gradient across this direction, and then that's going to give us Bernoulli's equation. And that means that the fluid's going to flow faster here than it does here because we have two different pressures here. And the pressure is going to be less here than it is here where it's going slower. Then the other example is, oh, what if it's going this way and the velocity changes as I go from top to bottom and then back again, and it goes like 0 to some maximum value back down to 0 again. That's also a gradient of velocities. So then there's a pressure gradient this way across that area that I can use to relate to a force. And I use the Newton's laws along with the concept of viscosity being a type of frictional force to relate that constant viscosity or friction force to the flow. And then it's this steady situation like when you push a block and the block slides along the ice and it starts sliding along the ice at constant velocity. Or a person jumps out of a plane and they start falling at constant velocity because the drag frictional force of the air is equal and opposite to their force of gravity that's causing them to fall. So then they just reach a constant, steady velocity without any acceleration. So that's something that you can note about this equation. This also describes a type of flow where there isn't any acceleration going on. It's all going at constant velocity. Okay, and it's named after a scientist who studied blood flow, who was very interested in medicine. Now, the quantity delta P over L, this quantity here, this is called a pressure gradient. And it's the pressure change per unit length, or the slope of a pressure graph. So it's a derivative. It's like delta P per unit length. And a large pressure change over a small distance is a large pressure gradient. And we can interpret Poiseuille's equation as saying that a pressure gradient drives a fluid flow. So this is our first introduction that gradients drive flows. So that's an important concept in physics. What do I mean by gradient? I mean, like, we kind of have like a vector field here. It's like, okay, so I have a gradient. It's like I have some minimum value here and some gradually increasing value to some maximum, and then it comes back down again. So it looks like this. So it's like pressure, it looks like this, where it's like, okay, reaches some minimum and then comes back up again. Because the pressure is greater in the spots where there's very little velocity, and then it becomes less in the places where the velocity is highest. So there's less here. So then I can take the derivative dp by dx, where this is x. This is some distance, x, or some distance, L. You make your choice. And I can compute that gradient along that distance, dp dl. So taking the slope of that at any of these points, the slope here, that's my gradient. It's like there, and there, and there. Okay? So that's what they mean by gradients. And so these gradients of velocity and pressures, they drive fluid flows. Okay, and then a surprising consequence is that there's a very strong dependence of the flow on the tube's radius, r to the fourth. That's interesting. So the flow rate is proportional to the fourth power of r. Fairly small changes in the radius have a large effect on the flow rate. So if I make this radius really small, what's going to happen to the flow rate? Is it going to increase or decrease? Decrease or increase? If I make r really small, is it going to increase or decrease? Where this is the flow rate. Who thinks increase? Raise your hand. Who thinks decrease? Okay, good. Yes. So it's going to decrease the fluid flow because it's like a fractional power of what it started with if it's decreasing. It's like 1/4. Okay, 1/4 to the fourth, that's way smaller. So there you can see how it's affected by that. Okay, great. Okay, so I think that's all for today. And we'll get into the physics of clogged arteries next class. I'll see everybody on Wednesday. We have a holiday on Monday.